Hi everyone, and welcome to another NL seminar. Thank you so much for coming at a non-standard time. And I'm very grateful that you're all here. Our speaker today is Justin Cho, who most of you know. He's in John's group here at ISI. Justin Cho is a PhD candidate at the University of Southern California, advised by Jonathan May. His research is centered around refining the context in which language models are involved in human AI interactions, such as enhancing dialogue models with grounding techniques and understanding of the interaction modality, personalizing language model outputs, and applying them for social good. He has previously led USC's team into the semifinals for the 4th Alexa Prize Social Bot Grand Challenge, co-organized the Conversational AI Workshop at ICML 2024, and interned at Meta's Conversational AI team, Amazon Alexa, and Amazon AGI. Today, he'll be talking to us about contextualization for human AI interactions. So please give it up for Justin, and we're very excited for your talk.
Awesome. Thank you, Katie, for your introduction. Good afternoon, everyone. My name is Justin Cho, and I'm a PhD candidate at USC-ISI. Thank you for this opportunity to share my work on improving contextualization for human-centric agents. Forgive me, I'm a little bit under the weather, so if my voice is a little bit jumbled, just let me know and I'll repeat myself to make myself more clear. Yeah, so throughout this talk, I'll be covering various work done with my wonderful collaborators across USC, ISI, Meta, and Amazon over the years of my PhD. Please feel free to interrupt whenever if you have any questions. Cool.
Sorry.
Cool. So I remember in the early years of my PhD, mainly working on improving dialogue models. My work focused on making dialogue models generate sensible and specific responses to just keep the conversation going. Considering today's standards, it was a pretty low bar, but still a popular research direction. I wonder who here remembers the days of Microsoft's Dialog GPT, Google's Mina, Lambda, and Facebook's Blunderbot.
Yeah.
I guess I can't really see the room, but anyways, it seems like there's a couple. So yeah, and then ChatGPT came along, and conversational AI quite suddenly seemed solved, became a commoditized utility shortly after it was released. It turned out then rather than doing dialogue-specific training, scaling up pre-training to build large language models and post-training with instruction and preference data was more effective for building conversational AI, and many followed suit. The initial reaction to these advances were that they were magic. Their general utility made them promising tools for more ambitious use cases. Apart from the most prevalent use cases of general virtual assistants, some simulated entire worlds, using them as world models, while others use them to develop automatic negotiators or even power robots to complete very simple tasks. But with time, expectations are lifted, goalposts move, and I think reality is set in. So this response, for example, that asks whether coffee is good for you might have looked fine when ChatGPT first came around and people were actually quite impressed. But how does this same response look if we imagine that this response was actually spoken back to us through a voice-based assistant instead of reading it through a textual interface? I don't know about you, but I don't think I have the patience to listen to all that, especially if that's how the assistant will be responding every single time. And what about if I had some medical condition that I should watch out for? What if I like to see scientific evidence backing up the information being provided? Also, another important context is being aligned with a higher level objective. So in this example, while the simulated support sounds empathetic, providing some like generic comments instead of properly establishing common ground with some questions can actually harm the user experience for tasks like therapy. So hopefully by now I've convinced you that utility is a function of context, which refers to any factor related to the situation which something exists or happens, and that we use a whole lot of this context to communicate and take on complex tasks. I've compared examples of how, who, and the what or why dimensions. Skip the when and where, but you can easily see how these are also important. So the problem here is that there's a lack of contextualization in these language models compared to humans. But when you consider the current training and evaluation paradigm, this lack of contextualization really isn't that surprising. The need for scale and collecting high quality instruction and preference data, along with the rapid progress in the field, the high stakes involved, we've come to choose what's readily available and convenient to collect. This means having a bias for textual data, instructional data with transactional interactions that are mostly single turn and direct, collecting simplified preferences without considering all the nuances, and only evaluating on easily verifiable evaluations. Not only, I guess, but mostly prioritizing. So these factors have all contributed to our lack of understanding for communicating with other modalities, excuse me, misalignment with individual users, and also not properly grasping higher level objectives that are accomplished over multiple turns and that are not always immediately verifiable. So given this understanding of how language models and their evaluations lack contextualization to be considered useful for broader real world cases, I want to go through some of my work that address the challenges with contextualizing LMs, language models for human AI interactions in mainly three dimensions, by expanding their understanding of the interaction modality, the how, and adapting to the specific target user, the who, and modeling real-world tasks with higher level objectives, the what or why. So I want to give you an overview of my overall PhD journey so far. Here's some representative work. The ones that I'll talk about today will be the ones in bold, but mainly I'll be talking about the how, who, and what and why. So first research question that targets the how is, can we contextualize language models for human AI interactions beyond text? The next one is, how can we make human AI interactions more personalized? And the last one would be, how can we model real-world tasks with higher level objectives? So let's start with the first research question. The first work that I'll be talking about is speech-worthy instruction to language models with the subtitle, Is Your Language Model Worth Listening to? So let me start with an example. Joe finds language models really useful, so he wants to be able to use them more often and hands-free, especially when he's driving. So he gives them a voice by equipping them with text-to-speech and gives it a test run by asking a question. My friend is expecting a baby boy in March. What should I give him as a present? So the ChatGPT or the likes of them might say something like, that's exciting, here's some great gift ideas, blah, 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 and give you this list that's not really easily verbalized. And so before getting to the full answer, Joe actually might be quite frustrated, and the response might have been totally fine for him if he actually read it through a screen. But he quickly ran out of patience when he had to listen to it because he can't navigate to the part that he's most interested in, and also the response simply isn't natural for a speech setting. So we first verify that Joe's problems are not just his own by asking annotators to evaluate two samples of question and answer pairs, one given in the text and another given in audio. So each annotator reads a answer and rates responses along 6 dimensions on a scale of 0 to 2, and then also does the same for an audio-based response. And these orders can be switched around to control for order bias. The first 3 is pretty standard from alignment literature, which is relevance, helpful, accuracy. But we've added 3 more because of our understanding of audio as a serial and transient mode of interaction. So the amount of information, informativeness, length, and understandability. For the first 3, we don't really see any significant difference. Responses are considered similarly relevant, helpful, and accurate. But when it actually comes down to the amount of information presented, the length of the response, and how easy the response was to understand, we see a significant drop across all of these three dimensions for audio. So Joe wasn't alone in thinking that language models are suboptimal for speech-based interactions. So the big question is, how should a response be different for voice then? A general rule of thumb would be something that, is minimally sufficient so that it's not too long, but then is also easily understandable. It should also definitely be helpful, and also engaging by asking an appropriate follow-up question so that it breaks up the amount of information that's being delivered. But that's just a general empirical hunch. Is there something that we can do more methodologically? So our first method is a tuning-free method, which uses prompts and in-context examples, which is arguably the easiest method out there if we just know how to prompt them. Here we leverage rule of thumbs from rule of thumbs for how to compose responses or how to compose content for audio based on best practices shared from the radio industry and listenability literature, and distill it into a prompt with some examples that abide by these instructions. But the limitation here is that these are mostly empirical findings that aren't specifically data-driven and not developed by thinking of voice assistant interactions in mind. So to take a data-driven approach, we think about teaching models with preference data that actually reflects speech-based preferences. This means that the users provided their preference after listening to responses rather than reading them. So to collect this data, we first extract user queries from instruction following datasets that are suitable for speech-based settings. So user queries like write a scene between two actors discussing the movie Inception are removed because you don't really expect that to be asked in a voice-based setting. Then we use various system prompts that span a spectrum of details on what speech suitability is in order to get a diverse set of responses that span different levels of speech suitability. And they can range from very simple to all the way to the detailed ones that we mentioned before that was used for the prompt from the radio industry setting. And we also use a various set of language models such as GPT-4, 3.5, Falcon to generate diverse responses. And then the responses are transformed into audio using text-to-speech, and then use this setup to collect a response such that the preference data has really wide coverage of what it means to be speech suitable. Annotators then listen to the two responses, which are presented in random order to control for order bias and indicate which they prefer more and why, which finally leads to our dataset called SpeechRef, which contains 20,000 speech-based preference data. And we can use SpeechRef to fine-tune Falcon 7B and Almo 7B with both direct preference optimization and proximal policy optimization. And we evaluate these models using pairwise comparisons by human evaluators, the same way if we've done the preference annotations. Any questions so far before I go into the results? Cool. So the main results that we see here is that all of our methods that we've proposed, which is the in-context learning with prompts and the preference optimization method, is that all of them lead to improvements, but actually, to our surprise, in-context learning actually is even more effective than preference optimization for these models that we fine-tuned. I think the most interesting thing, though, is that we find that combining both in-context learning and preference optimization actually leads to the best performance. We only show DPO performance here because PPO results are actually show the same trend. This means that each of these methods that we propose actually have additive improvements. To understand the nature of these additive improvements, we qualitatively examine the cases that DPO ICL wins over just using ICL and categorize them into frequently observed patterns. The first pattern that we see is that the DPO ICL responses are more conversational and contains better follow-up questions. So in this example, with a simple question asking about do RVs have bathrooms, the Falcon DPO ICL is a little bit more natural, actually saying yes, and then asking another follow-up question that can lead into a follow-up discussion. Also, DPICL generally leads to responses with more suitable lengths. This second response from Falcon ICL is actually truncated, but it goes on for a much longer time. But information-wise, it's kind of similar in what it provides, what it offers. And also, what's important is that DPICL is a lot more consistent in not providing any nonverbal text. So in this example, Falcon ICL, even though the amount of information or they fulfill the same goal, the Falcon ICL example contains a numbered list, which isn't really great for actually verbalizing. Next, we test whether we can improve black box models that we can't fine tune using our prompts and in context examples. When testing with GPT-4, these models lead to massive improvements over the vanilla GPT-4. So impressive that they actually beat our fine-tuned models, even when we combine both of our methods. We find that small models using both methods isn't enough to beat larger models just using ICL. But we want to understand why this is the case. And it actually is a bit of a more nuanced result, where GPT-4 ICL is preferred over our models most of the time just because it's more knowledgeable and more relevant. So controlling for this factor is actually a little bit difficult when you compare against different models instead of the same model class. Because questions like, what did the 0 say to the 8, obviously is sort of asking about a joke. And GPT-4 ICL is able to actually pick up on this, while Falcon completely fails because you can say that the base model just fails to understand these kind of implicit jokes. Other cases that the response is more comprehensive. So Falcon DPO ICL, mainly because maybe due to its fine-tuning process, it actually leads to over-optimizing brevity, such that the answer is really just a half answer or a very empty answer, just saying Spain is a wonderful place to live if when asked whether Spain is a good place to live. While GPT-4 ICL, even though it generates something much longer, actually offers a comprehensive answer. And similarly, there's sometimes cases where Falcon would also just say, I would love to help you on this particular problem, but then proceeds to just ask about a follow-up question without actually answering it. So these cases are prompted by GPT-4 ICL, even though there's a non-verbalizable content in the GPT-4 ICL response. But on the other hand, GPT-4 still lacks the kind of consistency that we see in the models that we fine-tune, which is mostly in being colloquial and providing nonverbal text. So in this example, when the response quality is more or less kind of similar or comparable, Falcon DPO ICL is more often preferred because it actually contains content that can be verbalized. Cool. So the highlights of this work is that we developed 2 methods for adapting language models to a new interaction modality to an entirely new context, which is speech. And the way we've done this is to collect a bunch of best practices from radio industry and listenability literature to distill it into an in-context learning problem that contains representative examples, which turned out to be a very low effort but high return approach. And then we showed preference optimization, which is to collect direct preferences that directly reflect preferences for the target modality that we have in mind. Interestingly, we find that combining them both actually leads to the best improvements, showing that there's non-overlapping gains, additive improvements. So based on our findings, I recommend starting with ICL and then refine with preference optimization to further improve consistency and reliability, which would be important in a lot of industry or product settings. Awesome. Any questions before I go on to the personalization aspect of context? I don't see any raised hands, and I think the room's muted. Okay.
Justin,
Yeah.
I think you.
Yeah, I can hear you now.
Oh, okay.
Just to make, this is the thesis proposal practice talk, presumably, right?
Yes.
Okay. You sure you want questions mid talk?
Is there a reason why I
Probably should wait
shouldn't?
until you're done with the talk to get questions, other clarification questions.
Oh, just to make sure I go through everything?
Yeah, it's kind of like standard approach.
Okay, sounds good to me. I just didn't know what was standard, so all right, in that case, let me just power through and then save questions for last. Okay, so I'll move on. The second research question looks at the who of in the context of human AI interactions, and this means whether what can we do to make human AI interactions more personalized. And so for this, I'll be presenting my work that's done with Amazon recently. Oh, hey, I actually used a transparent background here. Should have used that back in the beginning as well. But anyways, our lab logo. But yeah, the work is called Tuning Free Personalized Alignment via Trial Error Explained in Context Learning. I know that's a mouthful, but hopefully the work itself actually is kind of simple and easy to understand. Let me introduce the problem first. We want to work on personalized alignment. And what does that mean? So this means that we want to get from generic outputs from models to something that's more personalized. So if I want to write an email to respond to something like this particular topic about gender discrimination still being an issue in the United States today, I wouldn't want something that's very generic, has a lot of structural text and very formal, saying thank you for reaching out with your question, using fancier flowery words like crucial, relevant, and significant. It's kind of empty, and then all these structural words like to address your query, moreover, and then being super polite again, saying thank you once again. I don't think this is, I'm not saying I'm not a polite person, but sometimes this is excessive, right? And so I would want something a little bit more direct that reflects my style. I'm not saying this is my style, but it's just an example that's a little bit more stylized. Asking rhetorical questions. How often do you see people challenging their gender roles? Not often. Very short sentences. And then having a lot more opinionated phrases that's not seen in the generative case. Yeah, so hopefully with these examples, you can see what a personalized text looks like compared to something that's very generic. There are some important constraints for trying to do personalized alignment, though. A naive solution would think about using supervised fine-tuning with lots of per user data, but if you have worked in personalization, you would know that this isn't really feasible in most cases. There's just simply not a lot of personalization data. For each user, to ask for them to provide a lot of personal data, it requires too much effort that they're just not willing to provide, or there's privacy concerns that prevents you from using them. And so we want to work in a practical setting where the data requirements enforce us to be in a low research setting using less than 10 samples per user, and assuming that we only have access to a single user's data at a time. We're not using a whole pool of user data to train on for all users, but a single user at a time. So first, I'm going to introduce a word called ditto, which is work that I've done with Omar from Stanford on iteratively fine-tuning with synthetic data. And it's called demonstration iterated task optimization. But the idea itself is quite simple. You start off with just doing supervised fine-tuning, even with a very small sample of user demonstrated data, so personal data, to shift the model towards a particular user behavior. And then you generate text with that fine-tuned model. And any text that you have generated in step 2, you assume to be worse than the gold example, the user demonstration that you used in the supervised fine-tuning step. And so you use these combinations, these synthetic combinations, to create a preference data set and use it for preference optimization. And then you can repeat steps 2 to 3 until convergence on a validation set. This idea is actually kind of similar to some other similar work. And I sort of use this umbrella term called trial error fine tuning because the whole idea here is to actually generate some errors, try doing a particular task and use those as errors and use that information to further fine tune a model based on these trial and errors to hopefully teach the model to avoid these kind of errors. Cool. And so, oops, I have these weird artifacts here, but ditto results. Before I show them, I wanted to share how the evaluation is done. It's a LLM, a language model as a judge kind of setting, where the language model is shown some author examples and then shown some options. One from option A from one other model and option B from a different model, and then ask the model which one of these A or B is more similar to the author's actual text. And with this language model as a judge setting, we see that Ditto actually is able to beat a lot of very competitive baselines, including GPT-4 using Few-Shot. And here it's notable that Mistral was used for Ditto with a 7 billion parameter model, which is much smaller than GPT-4. So that's cool and all, but the problem here is that this method requires fine-tuning. And actually fine-tuning is impractical in many cases for the best language models. Either they're black box, you simply don't have access to their model weights, or they're extremely large, so that training them causes a lot of overhead, requires a lot of compute. And also, if you fine-tune them for individual users, then you have individual per user weights that you have to manage, which leads to a lot of overhead. So the problem that we want to tackle is whether we can develop a tuning-free equivalent of Ditto. And so the general pipeline of Ditto or tuning, trial and error fine-tuning is shown here above. So you start with supervised fine-tuning and then generate failures, and then you use the failures to do preference optimization. And the challenge here is how can we substitute supervised fine-tuning, substitute the DPO step, and also how can we accommodate different iterations within a given context window, because this process can be repeated multiple times. And this is where our solution comes in. We call it trial error explain in context learning, short TICL. And the first step here is to replace supervised fine-tuning with Few-Shot ICL. So this is kind of simple. You just have an in-context learning example that contains the same examples that you see in supervised fine-tuning, but instead of fine-tuning, you just put them into the context and then ask them to do the last task. A little note here is, oh, actually, never mind. Yeah, and then the next step is to generate some outputs with a TICL prompt. For the first iteration, this is just simply the same as a Few-Shot in context learning example, like for supervised fine-tuning, the equivalent to supervised fine-tuning, because we didn't generate any negative samples yet. So this is not that different. But then the next step is to replace DPO with prompt augmentation that includes negative examples and explanations. So if you see here on the right, under the pinkish area, that instead of just containing the good examples with the green check marks, you generate negative samples, which are the ones in the red X check marks. And then you have this delta, the yellow box, that contains explanations that explain how the failures, the X's, compared to the ones in the check marks. And so you use this full set of information to now perform the target task. So you can see how TICL doesn't include any kind of parameter updates, but it's completely tune-free. One problem here is that if you repeat this process multiple times, you will quickly have a very long context, which is not ideal for efficiency issues. And so we added verifier here. The same setup as the language model as suggested that I showed before, that decides to only keep the negative samples that are actually negative. So if they believe the negative sample is significantly, is differentiable with the good example, the green one, then it's actually included. If not, we just discard it. So then after all these processes, we iterate through multiple times, and then we evaluate on a validation set. At test time, we use tickle prompt with a full training set that we've accumulated over the iterations. And so I want to share the results of our approach across the board for two data sets, CMCC and CCAT. We see higher win rates, even compared to Ditto, which is a fine-tuned model, when using both GPT-4o and Claude 3 Sonnet. You can see the Ditto results in the purple, and then you can see the same model class performance in the respective colors. Blue is for GPT-4o, and green is for Claude 3 Sonnet. And Tickle also outperforms all other competitive inference-only methods within the same model class. So like simpler methods like FewShot or more complex methods like Chain of Thought or OPRO are significantly worse than our method Tickle. We want to understand why this is the case. Why does Tickle provide such performance gains compared to a simple approach like FewShot? Aren't models supposed to be able to pick up on the FewShot examples on just when they're just given the good examples? To understand why the performance differences between Tickle and FewShot ICL, we do a lexical overlap analysis using a fighting words model. The fighting words model just looks at the frequency of words or n-grams that occur between the generated text between these two models, and then compare which ones are statistically significantly more frequent for one model over another. So hopefully this Venn diagram here kind of makes sense, where the A/B shows text that is unique or statistically more significant, more frequent for Tickle, and the other side is text that is more frequent for FewShot ICL. And when we look at these examples, the frequent n-grams on Tickle's side are more of the simple words and opinionated words like honestly and casual. So why? And when we measure the readability of these n-grams for Tickle, the readability score is very high, meaning that these words are super simple, mostly single syllable and easy to understand. But when we actually flip and look at the other side, the frequent n-grams for FewShot ICL are the formal and structural words like additionally and therefore. And you can see that the readability score for them, for these words, actually drop a lot to 36.62. By the way, higher the better for readability score. Yeah. And if we look at some actual qualitative examples, we can see that this is indeed the case, that Tickle is actually a lot more effective in overcoming bias for these formal and structural phrases that are found in the base model, and instead elects the casual and opinionated phrases from the user examples. So here on the top side, top right, you see the FewShot ICL producing a lot of these words in red. Even though these kind of examples are from the authors were given in context, the model still decides to use words like fundamental, ultimately, hence, and in regards, while Tickle is able to use a lot more of the opinionated and casual phrases better. If you recall the results, though, another interesting thing that we find is that Claude 3 Sonnet is a lot better than GPT-4o, even though in other language model bench leaderboards, we see the opposite for completing tasks. And we kind of want to understand why this is the case as well. One thing we do here is we decide to swap different components of Tickle with different models. So first configuration is to swap GPT-4o's explanation model, the model that generates the explanations, with the other model. So using GPT-4o with Tickle, but only replacing the explanation step with Claude 3 Sonnet and vice versa. Swapping these explanation generation models, we see actually a little performance difference. So this means that explanation quality is actually similar. So next, instead of just replacing the explanation model, we think about running through the full Tickle cycle and then just using a Tickle prompt that's been used by one model, developed by one model, and using it with a different model. So we run Tickle for GPT-4o and then use that prompt with Claude 3 Sonnet and vice versa. So swapping the fully formed Tickle prompts, we actually see a large drop in performance compared to the no swap, the base setting. And so this is actually kind of interesting. It means that the models need to see their own failures in order to overcome their own biases. And seeing some failure cases from other models that aren't relevant to their own generation distribution, it doesn't help as much. I've also, so we repeat the kind of lexical analysis here as well, but I think overall the main finding in terms of why Claude 3 Sonnet does better than GPT-4o is similar to how GPT-4o Tickle was better than the Fuchsia ICL equivalent by generating more casual phrases better. So the highlights of this work is that synthetic negative examples and the corresponding explanations are very effective, even in low resource settings for personalized text generation. Our method that we propose, Tickle, is helpful because it overcomes bias for formal and structural language in the base model, and instead actually uses the opinionated and casual phrases that is seen in the user examples. We find that by comparison Claude and GPT-4o, that language models need to be shown their own negative outputs in the context for Tickle to be effective. Failure cases from other models are less effective. All right, how am I doing with time? I think I'm good. Okay, cool. So the last part is RQ3. How can we model real world tasks with higher level objectives? And for this, I'll be presenting our work from EMLP NACL 2020. Oh, I have the conference wrong. It was actually for EMLP 2023. Can language model moderators improve the health of online discourse? The backdrop of this work is that effective moderators have become more important now than ever. We have seen societal polarization worsen over the recent years, bolstered by social media algorithms amplifying biases and the proliferation of fake news and bots. So generative AI will most likely further accelerate the increase in amount of online content. So having effective moderation strategies is more important now than ever. But how do we go about doing moderation? The most prevalent approach is actually oversimplistic. Let's look at an example from a conversation on Reddit discussing the relationship between beauty and health. So user A here becomes agitated and aggressively attacks user B for thinking that being poor contributes to bad health. Given that this comment has been flagged for moderation, those platforms take one of two approaches. One is to delete the comment entirely, and the other is to ban the user if a similar offense has been repeatedly made. So either way, this kind of silencing can push user A to seek an echo chamber that shares the same thoughts, preventing the opportunity to reconcile differences in opinions in a constructive way. The alternative to these iron-fisted approaches is conversational moderation, to actually engage, where a moderator intervenes in the conversation and provide guidance that's specific to this current context to encourage more civic discourse. The moderator may say something that expresses empathy for users' safe frustration, showing understanding, but yet suggests a response that is more grounded on evidence rather than strong emotions. And this can help user A tone down charged emotions and continue the discussion in a more constructive way. While this is a better approach to moderation, you can imagine how repeatedly dealing with this kind of toxic behavior and suggesting context-specific alternative behavior can quickly get taxing. So this approach is not scalable. But there's hope. The rise of general purpose language models in recent years show that there might be something that we can automate here. As much as these models are harmful for the quality of online content and adding, potentially fake news and whatnot, they present a unique opportunity to also improve the online experience. They can be leveraged instead to assist humans, human moderators, by automatically suggesting responses. This can significantly relieve their burden of developing their own responses from scratch for each of the numerous cases that they need to handle. So given this landscape, we seek to answer two research questions that shape our work. First is, how should we evaluate language model-based moderators as assistants that can scale up the efforts of human moderators? And once we establish the how of this, how to go about doing this evaluation, we want to know whether language model moderators can provide specific and fair feedback to make online users more cooperative and respectful. So let's dive into the first question. How should we evaluate conversational moderation effectiveness? We find our answers on how to do this from moderation literature. So Grimmelman established that the most important objectives of moderation is to make online users more cooperative and respectful of one another. But in addition to these main objectives, Kiesler et al. Found that when moderators provide specific and fair feedback, users are more likely to accept the moderation event, such as having their comments deleted or being suggested an alternative course of action. So in our work, we evaluate language models across these 4 dimensions. We want to be able to evaluate for these dimensions while fulfilling certain criteria that reflects realistic constraints. First is that the study should be as realistic as possible in terms of in how it studies the moderators under a realistic context so that the results are generalizable to the real world. Second is that our methodology should be safe and that it doesn't harm any real unwitting users. And lastly, it should be well controlled so that we isolate and measure the effectiveness of the moderator. This means removing other potential confounding factors as best as possible to solely focus on the moderator's role for measuring the evaluation criteria. So building on these dimensions, we propose our evaluation method. First, we extract conversations that contain controversial comments from Reddit directly. We use a controversial flare provided by Reddit's API, and then further filter them using GPT-4. So this fulfills the realistic criteria where we start with a real controversial conversation to replicate highly charged conversations. Then we take these conversations and have them be continued between a human participant that acts as a moderated user and our moderator bots. This fulfills the criteria of safety, as this lets us not affect any real users and only work with human participants that are fully aware of the task and provide a consent ahead of time. And lastly, after the participant and the moderator completes the conversation, the evaluator answers a series of survey questions about the evaluation dimensions. So if the evaluator is the same as the conversation participant, then this evaluation is done in a first-person point of view. If not, it's done in a third-person point of view. This is important actually to let us study the moderator's effect on the moderated user's perceived influence of the moderator, as opposed to the perceived effect on the moderated user in the perspective of the bystanders. So we want to be able to study both cases because they are both important stakeholders in the online communities. Ultimately, we see language models recommending responses to human moderators rather than directly intervening as moderators due to safety concerns. But we intentionally choose this approach for our evaluation of directly interacting with moderator bots in a dyadic setting to focus specifically on the usefulness of the moderator bots' responses themselves. This is important because it helps us remove confounding factors such as variances in how each human and moderators decide to choose the moderator bot's responses, and also the decision, a separate decision of when to moderate. Cool. So now that we have established our evaluation methodology, I want to answer the question of, can language model moderators make online users more cooperative and respectful? The experimental setup here is that we have each moderator bot evaluated with 20 seed conversations, each continued by 3 different human participants. And afterwards, the human participants rate on a Likert scale from 0 to 4 for each of the survey dimensions that I mentioned before, the fair, specific, cooperative, and respectful. Some of the baselines that we examine here, apart from our models, is pro-social dialogue models, which are trained to exhibit pro-social behavior. They are based on T5. Cosmo XL model directly generates the Cosmo XL model directly generates pro-social responses, while the Canary plus Cosmo XL Cosmo XL model takes a two-step approach that generates pro-social rules of thumb first, and then generate the response. So these two models, to be fair, are not explicitly trained to perform moderation, but there are many similarities between pro-social behavior and moderator suggestions, so we include them as baselines. The other approaches are the GPT-based prompted models. The baseline here is the prompt that you are a moderator. But then we look at other more complex kind of prompts that are grounded in the literature that have been found to be useful for conflict resolution, such as nonviolent communication. Nonviolent communication is is a method for conflict resolution that emphasizes empathy as the main principle. Another is Socratic dialogue, which uses techniques for cognitive behavior therapy. It encourages self-reflection and grounded statements to supporting evidence. So the way we develop these specific prompts to embody these behaviors, to make sure that they embody these behaviors, is we use a self-chat setting where we simulate a conversation between a moderator and a moderated user, and we qualitatively examine these sample completions and make sure we refine the prompts until the desired behavior for Socratic dialogue and NVC is actually reflected in the conversations. Here are some example responses. For the sake of time, I'm not going to go through each one of them, but one thing to highlight here is that the Socratic dialogue model actually leads to the longest responses that actually considers both sides of the discussion. So it considers both viewpoints of A and B here, while the other ones remain kind of simplistic. And you can look, for example, the baseline ones just says, something generic. Thank you for contributing to the discussion. It's important to have differing perspectives, but be, civil and respectful. So it doesn't really dive into any of the specifics of the given conversation, while NVC and the others tend to do so more. So going directly into the results, the first person point of view evaluation is, as a reminder, where the evaluator is the moderator user, and it measures how the moderator user think of their direct experience of being moderated. Here we can immediately see that the GPT-based models largely outperform the pro-social dialogue models in all dimensions. This is because we often see that pro-social models don't directly do moderation. And while they do suggest being civic and being more civil and respectful, it's not very consistent. And they might actually fight back in certain cases, making the conversations even worse in terms of conflict. But yeah, that's what happens there. But among the GPT-based models, Socratic dialogue model actually outperforms all models in all dimensions, doing especially well in providing specific and fair feedback. So on a scale of 4, you can see the Socratic model getting consistently over a 3 in terms of both being specific and fair. But when we move into the cooperative and respectful aspects, the actual dimensions that we really want to see change, all models seem to kind of, in relative terms, struggle, with all scores remaining under a 3. Oops, okay, yeah. And so moving on to the third person POV point of view, where we have evaluators that are not the participants that continue the conversation. So they see the full conversation and then evaluate how the moderator performed. So this measures how the observers of the conversation perceive the effect of the moderator on the moderated user. So the figure on the right shows that while these third-person evaluators provide similar scores for how specific and fair the moderators were, they provide much lower scores for how effective they were in making the moderated users more cooperative and respectful. So while the overall ranking and relative performance of the models remain roughly the same between the two perspectives, this result shows that it is important to use the same point of view when making head-to-head comparisons, and also that considering these two different perspectives are important when doing this kind of evaluation. Considering all stakeholders is important. One thing that we're also really curious about is whether we can use GPT-4 as a judge, so that we don't expose humans to these, conflict, these highly charged conversations that can be emotionally taxing, and whether we can get kind of similar signal from language models if they were to perform the same task. Results actually show that the scores are quite similar to those of the third person point of view results, but they tend to be a lot more generous in scores, especially for the pro-social dialogue models that scored very low in human evaluations. They were getting scores well below 1, but here they are scoring above 2. Above 2 in quite a few dimensions. More importantly, the relative performance between these models are not the same as those that are seen in the human evaluation, meaning that the resulting ranking is different. So this isn't helpful for choosing which model to actually use for this particular task. Main takeaway here is that although the general trend seems, there seems to be some correlation, it's not a reliable substitute for human evaluation for the time being when it comes down to deciding which of these models to actually use to help humans, human moderators. So the highlight here is that we establish a framework for how to evaluate conversational moderation in a realistic, safe, and controlled manner. And we find that accomplishing objective and surface level goals is feasible, such as fairness and specificity, but achieving the higher level objectives, being cooperative and respectful, is a lot more challenging. And then there's differences in results based on the point of view, which highlight that comprehensive evaluation that considers all the stakeholders for a particular task is important, and language model as a judge for subjective multi-turn tasks remains challenging for now. Cool, so in summary, these are the works that I've walked through today, answering these 3 research questions and introducing one represented task paper for each one of them. And to wrap up, I want to talk about the future directions that I'm excited about. So I feel like we just started scratching the surface, and there's exciting times are ahead. First, we're still mainly confined to text-based assistance, and there's so much more that can be done by omni-model assistance. And I feel the path for that is to maximize the shared context between these assistants and the context that we have. And this can help minimize information asymmetry and therefore maximize utility. The main ways that I see ourselves getting here is first, providing complete context based on a full understanding of the full spectrum of human communication. So this goes beyond just text and where I talked about speech, but also other multimodal kind of sensory inputs. And also we want personalization to occur in a omni-model and omni-domain way. Previously, we've been mostly confined to textual personalized data, but there's so much more personal data in various forms that could be used here. And finally, there's growing work in improving simulations to become high fidelity. And this helps us tackle real world problems that might be challenging to do in the real world because of ethical issues and whatnot. And through simulations, we might be able to tackle them in a more scientific and safe manner. So to go into a little bit of detail for each of these, for understanding the full spectrum of human communication, the kind of angle that I'm looking at is nonverbal communication. Nonverbal communication is the transmission of information without using spoken or written words. And this includes body language, gestures, mime, tone of voice, appearance, and so on. And NVC is important because it's a communication channel that is often actually more important than verbal communication. There's prior work that has shown that if there are inconsistencies between what I'm saying and what I'm showing in terms of my body language, the true intent is actually measured by the body language more often. And also, if we want to make AI more user-friendly, and for us to make stronger bonds with them, it requires a comprehensive anthropomorphism, because humans, when we make relationship, those are more often established by nonverbal signals. Also, NVC is also a crucial substitute to verbal communication for assistive and accessible technologies for people who can't hear or speak. And then you can imagine how it's also useful in cross-lingual settings. But this is a mammoth task. Like it's going to require a lot of work, because to understand everything that we express through all of our gestures and whatnot is in combination with what we say is going to require a lot of processing multimodal inputs. And I think the first direction here is to collect data sets and design evaluation benchmarks that measure tractable aspects of MVC. And I've already started work in this direction, where I've looked into MIME as a target task. MIME understanding as a target task. MIME here is any actions that is done without a salient object. So someone trying to kick a ball without actual ball present, or swing a bat without holding onto a bat, would be considered MIME. The reason why I look at these are because they have high universal agreement and reliable one-to-one mapping with the intended action, while other gestures like the thumbs up might be dependent on the cultural context. And so we want to answer whether vision language models can correctly identify the actions shown in MIME. And here I've started some work in collecting data using motion capture and using 3D graphic software to create various adversarial examples of mimed actions. The next direction for omni-model and omni-domain personalized alignment mainly is focusing on how to streamline the process of collecting personal data in a more low-effort way, and thinking about methods to use data that's been collected this way. So, prior work has mostly been limited to user-provided textual data for a narrow task. But if you can imagine how we can collect user interaction data through computer access or screen recordings or camera feeds from embodied agents. And so we'll likely require multimodal models that can handle long context, because now there's so much more information and there's a lot of work that's been started in this direction. And a crucial component here would be to consider safety in terms of how to balance between privacy and utility. Lastly, the high fidelity simulations for tackling real world problems. This stems from realizing that many real world tasks require multi-step interactions that take place under a wide variety of contexts. So we want to study them using simulations, and this helps us expose behavioral differences between humans and AI. And this is important because once we identify these differences, we can think about methods to bridge these differences to improve simulation fidelity, which then further improves which then can further accelerate research on complex tasks through simulations. And so we can accelerate, or we can start a virtuous cycle. And I've already started work in this particular direction. One is looking at using language models for simulations in a learning outcome estimation, where we have a language model student ask questions while learning content to see which kind of questions asked while learning is high utility, and another where we examine using language models to simulate news interviews to see which kind of strategies are best for extracting important information from different sources. So yeah, that's all for today. Thank you. I want to end with this quote that seems very relevant to my talk by Kenneth Noland that said, "For me, context is the key. From that comes the understanding of everything." And I can't agree less, given the current landscape of where we are with language models and AI systems.
I just unmuted it.
Yeah. Thank you so much, Justin. Are there any questions either in the room or from the Zoom attendees? Yes, John.
So going back to the first part of your talk, can you think about how you might do the same kind of work if instead of trying to communicate with speech, you were trying to make a model that would communicate with sign?
What was that again? Make it do with sign?
Imagine a sign language generation model, and you put a query in to the model you wanted to sign back at you. How would you maybe change any aspects of the way that you developed the speech-worthy language model? What would be considerations to take?
Yeah, I think it actually shifts kind of into a different domain when we think about science, because it's a different, at least with speech, there's still textual components that's just verbalized. But then when you go into science, it's mostly visual. And so I think the kind of preference data that we try to collect, or even the in-context learning examples here, might be completely different in how it has to go into these vision language models to be able to communicate them. I've started work with the MIME Understanding project, where I've seen that we can provide view context examples for even in the vision setting as well. But I've learned the painful way through API credit costs that even few shot examples for a very small model in vision is actually very expensive. So I think the overall method might be the paradigm of first starting with in-context learning and then looking into hopefully preference data for understanding these different, which kind of body language is more preferred over another, or signs is preferred, might still be relevant. But I think there will be a lot of like other technical improvements that need to be made for our methods to be similarly applicable for, sign understanding, for instance.
Are there any other questions either on Zoom or in person? Okay, well, I think that's it. Thank you so much, Justin. And we will have our next NL seminar 2 weeks from today on the 13th, also at this 3 p.m. time because of the speaker's travel schedule. And that will be with Arjun Subramanian from UCLA. Right. So thank you all so much for being here.
Awesome. Thank you so much, everyone. Yeah, I would appreciate your feedback on this talk because this is going to be the basis for my thesis proposal. So I appreciate any feedback offline afterwards. Thank you.